Okay, let's go and get started today. Today we're going to be continuing on with context-free grammars, but today we're going to look at manipulating them. And what we mean by manipulating them we'll get to in a second, but let's just dig in and get started. So the first thing is that different grammars can define the same language. So in other words, if we have some given language, there can be more than one grammar that defines that. And sometimes it can be useful to put the grammar that defines the language into some certain form to make things easier to understand or easier to use for certain kinds of things. So in other words, just like with regular expressions, where you could have a really complicated regular expression or maybe a simpler one, or maybe with DFAs, you could have one with a whole lot of states, or you can minimize it and have the minimum number of possible states. So that kind of manipulation of taking a grammar in one form and moving it into another form for some desirable reason is what we're going to look at today. And we're going to look at a few of those. So what we're looking for is a toolbox of methods of manipulating these context-free languages or context-free grammars from one form to another, and we want to do so in a way that does not change the language that we represent. So we don't want to change the language, we just want to change the grammar around without messing with the language. So let's look at a couple manipulations here, a few of them that are going to be useful for various circumstances. All right, so the first one is removing lambda productions. And so a lambda production is any production that's in the form A produces lambda. That's a lambda production. It's a cat fight breaking out. All right. Anyway, any variable A such that A eventually produces lambda is what we would call a nullable variable. So a nullable variable is one that could eventually, after one or more steps, result in the empty string, and only the empty string. So the idea here is that we're going to want to get rid of those productions. Now, there is one case where we can't get rid of that, and that's if S can eventually produce lambda, then we have to have at least one lambda production, S producing lambda, but that's the only one that's ever really required. If lambda is not in the language, in other words, if the language does not include empty string, then we can always get rid of all of the lambda productions in our grammar. If lambda is in the language, we can get rid of all of them except for S producing lambda. All right, so let's look at how to remove those. And essentially, there's a couple, just a two-step process here for removing lambda productions. The first one is identify all the variables that are nullable. In other words, any variable that could eventually produce lambda. Then we make a list of those. And then after we have the list of those, what we're going to do is we're going to go through and replace all occurring nullable variables in the right-hand side of productions. And so in other words, on the right side of there, over here, with combinations with the nullable variables both present and removed. And the idea here, that's going to make sense when we look at an example. So let's go ahead and look at an example. All right, so here's an example. First off, does this have nullable variables? Is there anything here that can produce just lambda? What about S? Well, S cannot produce just lambda, so S is not nullable. A, however, can produce just lambda, so it's nullable. And B can also produce just lambda, so B is also nullable. So we have two nullable variables, A and B here. S is not, because we do not get a lambda. There's no way to get a lambda by itself from either of these two productions. All right, so that was step one, is identifying them. Step two is rewrite the productions with and without the nullable variables on the right-hand side. So in other words, anywhere I see an A, I need a version of that production with it, and I need a version of the production where we just take it out. And anywhere I see a B, since it was nullable, I need to have a version of it with it in, and one of them where we just take it out. All right, so let's look at what that looks like. Okay, so here's what that looks like. Here's the production A, there it is with it in. And then if we take out that A and replace it with lambda, because A is nullable, it could just do nothing. So here's the version with it missing. And here's B, there's with it in. And here's the one with it out. Here's the A with the A in. Here's with it out. There's B, there's with it out. And the reason this works is because if you think about that, A producing nothing is the same as not calling A at all, not using A at all in that situation. But since A can produce things other than nothing, we still have to have it there as well. Now that's one other thing. If a variable only produces lambda, we can just delete it from the entire thing and cut it out of any production where we see it. But if it produces things other than lambda, like we have here, then we need to represent all of the possibilities of it with it in and with it out. And so this is the version of that same language. This is the same context-free language that this is representing, but now we have no more lambda productions. And you might say, well, why do we want to get rid of the lambda productions? And that's there are a lot of reasons why, but one of the ones that might resonate with you is like, why expand something to nothing rather than just not do it at all? And that's the idea here is it's kind of we're wasting time going to A to have it eventually do nothing when we could just not do that at all. Okay, now another type of manipulation that can be desirable to get rid of are what are called unit productions. And what a unit production is, it's one in the form where we have a variable producing another variable directly. In other words, think about this as like a function call, and what that function does is it just calls another function. That's it. So it doesn't make any progress on terminals or generating anything. It's just a variable being replaced by another variable. Okay, so to remove, there's a three-step process here. The first step, find all instances where we have a variable producing another variable. Any variable that could produce another variable with nothing else, just that other variable, we identify those. And then we rewrite by leaving out all the unit productions. In other words, any production that has a variable producing another variable, we just rewrite it without those. We get rid of those. Now, there's one other step though, and that's now we have to add in all non-unit right-hand sides from all reachable B for each A. So in other words, A can get to B. We have to write the right-hand sides of this in place of as new productions for A. And again, this will make more sense when we look at an example. So let's do that. Okay, so here's an example. So removing unit productions. So first off, I guess step one is here, find all the reachable unit productions. What are all the unit productions that we can have here? Whereas a variable producing a variable. Where here we have S producing A. That's one. S producing just C. That's one. A producing just B is one. B producing just A is one. C producing just A is one. And there's one other one here that's a little bit trickier to spot. And that is, notice that since S could produce A and A could produce B, S can also, after two steps, produce just B. S could result in just B. So all of the unit productions that we have, S can produce A and C and also B. A can produce B, B can produce A, C can produce A, C can produce B. Now let's look at all these one at a time. S producing A, that one's easy, goes right there. S producing C, that's easy, right there. A producing B, easy, A produces B. B producing A, B produces A. C producing A, C produces just A. C producing B, a little more complicated. C goes to A goes to B. So C by way of A could get to B, and the same thing for S. S can go by way of A and get to B. So this is the list of all of the unit productions that we found, all the reachable ones. So step two is to rewrite without the unit production. So we're going to, any of them where there's a single variable, we're just going to rewrite it without those. We're going to delete those. So in this case, we leave off the A, leave off the C, we're left with just that. In this one, we have the A and the B, leave off the B. This one, we have the B, but no A, we leave that off. This one, there's just an A there, leave it off. So in other words, we've just filtered out all the unit productions in step two. And now in step three, we're going to add the right-hand side from all reachable variables. So in other words, here is that thing. This is just a copy of that, but I've identified with different colors here, those different ones that are the right-hand sides. These are the right-hand sides for A. This is the right-hand side for B. That's the right-hand side for C. So in this case, for S, S could get to A, B, and C. So we need to add all of these in over here. So there are the ones from A added in. Here's one from B added in. There's one from C added in. A can only get directly to B. So on A, we need to plug in the one for B. So here's the right-hand side for B. We add that at the end. And then the one for B, B can get to A. So for B, we need to plug in the ones for A over there. So there are those two there plugged in from here. And then C can get to A and B, so we need both the ones from A and B added onto C. So there are the ones from A. There's one from B. Now, you might have noticed that there's a little bit of something strange that happened here, that we have some duplicates. We have the b, lowercase b production twice on S. We have it twice on A. We have b twice on B. We have b twice on C. And so the final step here we could say is remove any of the duplicate right-hand sides. B, 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 get rid of those duplicates. And that's going to leave us with this as our final grammar. So we're done. And notice there are no more unit productions in this, and we have not changed the language that this defines. You might ask the question, well, why get rid of unit productions? Why is that something we want to get rid of? Why is it bad to have unit productions? And think about that again from an efficiency standpoint. If you're having one variable just being replaced by another variable, being replaced by another one, why jump through all the hoops of going through the variables when we could have done directly what they were going to do anyway? So in other words, rather than having S jump to A to generate an A or B, why not just have S generate that A or B directly? So it saves steps. The other advantage of that is, notice here we have some weird things where A can go to B and B can go directly to A, and these things can just get stuck, not creating any terminals, not consuming any input. And so that would be another advantage of getting rid of these. When we get rid of all of that, we now notice we no longer have A and B jumping around to each other for no reason. So we don't have that cycle that could go infinitely there anymore. Okay, the next one that we're going to look at today is removing what are called useless productions. And useless productions are ones that, well, have no use. There's no point to having them in our grammar at all. And there are actually two forms of unit productions or useless productions that are that we need to think about. So useless production is one that is either can never lead to a sentence. And remember, a sentence is a string of terminals and only terminals. So it's a string of 0 or more terminals. So useless production will be one that you could never get a string of only terminals from if we take that production. And the second type is one that you could never get to. In other words, a production that we could never use anywhere. We could never get to a point where it could be used. So in other words, the two useless types of productions, ones that could never result in a string in our language, and one that we could never get to from starting with S. All right, let's look at an example here and then see if we can figure out which ones are useless by looking at this. So here's an example of a context-free grammar. We've got S producing AS, S producing BS, S producing A, S producing B. We do have some unit productions here, but we're not worried about that right now. We could get rid of those if we wanted to, but we'll just leave them in there since we're focusing on useless productions. And then we have A produces A, lowercase a, B produces lowercase b, B or B, and C produces A, B, or B, A, B. So which ones of these are useless? So let's take a second to look at it. So the first thing that might pop out looking at this is ones that could never lead to a sentence. This one here, A produces lowercase a, is always going to recurse back and make an infinite length of string of lowercase a's, eventually ending with this variable A. Well, that's never going to produce only terminals. It's always going to have this variable at the end. And once we take this path, we will never get a string of only terminals. So this is going to recurse endlessly. So that one is useless. So that means if that's useless, we need to remove any production that has A anywhere in it. Because if I take that path, I'm doomed to repeating over and over and over again and never getting to a string of only terminals. So that means I could get rid of this one, and this whole thing here, and this one down here with C. So we could get rid of all of those. Now, are there any other useless ones looking at this now? Now think about the second category. Are there any of these that we cannot get to from S? I'll give you a second to look at that. Okay, and in this case you might say, well, if we start with S, S can certainly loop back to S here, and it can get to B, and B only has the variable B. How do we ever get to C? We can never get to C here, so C is unreachable. and we can remove all of the productions for C, which is basically just all that down there. So we're left with what we have up here. S produces AS or BS or just capital B, and then B produces lowercase b, capital B, or just B. So we eliminated two variables and all the productions that use those variables, and now we have something that no longer has useless productions in it. And what remains is the result of that elimination. Okay, now we went through that example. I want to touch on it a little bit more and talk about it a little more formally, since we're going to circle back to this stuff a little bit later. But the formal view of this is if you have a grammar consisting of the four parts, variables, terminals, start production, set of productions, and it's a context-free grammar, then a variable A, one of our variables here, A, is said to be useful if and only if there exists some string W in our language such that when we start with the start production, we can, after 0 or more steps along a derivation, come to some form where that variable is inside of that sentential form. And then after 0 or more steps from that, we eventually get to a string W that's only terminal. So in other words, what we're saying is a variable to be useful has to be somewhere in a derivation or along a derivation to a string of only terminals, string that's in our language. So if it can show up in any sentential form, then it's useful. So any variable that's not useful is therefore useless, and any production that contains a useless variable, either on the left-hand side or the right-hand side, is itself useless. So to formalize the process of removing useless productions, let's take a little bit closer look at that. So step 1, identify all variables that cannot produce a terminal string. And then we eliminate any production that contains those. Step 2, how do we know which ones are reachable and which ones aren't? Well, we create a dependency graph using the variables, identify any variable in the graph that can't be reached from S, and eliminate any productions that are not reachable from S from both the left-hand side or the right-hand side. Just get rid of any production that has those. And step 3, profit. No, just kidding. There's no step 3. Step 1 and 2 is it. 3 is actually right out. Seriously though, let's do one more example of removing useless productions. And that should help. Now here's a little bit more complicated example. So notice we've got 5 different variables, S, A, B, C, and D. S is our start, and these are all our productions. So step 1, identify variables that cannot end in a sentence, or those are called non-terminable variables. In other words, are there any variables that could, once we take that variable and try to apply production, that it can never end? Well, let's look at them. S. Well, S can call A, S, B, and it can recurse, and it might be able to recurse infinitely. We're not sure. But if we look at S can take A, and A just produces AB, well, A is definitely terminable. And up here for S, the second one of these, that's only A, which we know is terminable. So S is also terminable. So in other words, S is terminable. A is terminable. B is terminable. You can tell that. There are no variables even on the right-hand side of these two. So those are definitely terminable. C is terminable. Let's look at D. D, we're not sure about, but A is terminable, but it's in a string where it also has D, which is not terminable yet. We don't know that. And then there's D again over here. So D is non-terminable. So D has every right-hand side has D in it. And there's no way for D to ever end. In other words, if we take path D, we're just going to be stuck here endlessly recursing through D, expanding it to include another D, and expanding it to have another one, and expanding it to have another one. And we're never going to get out of that endless recursion here. So non-terminable variables, or D, eliminate all productions that have D anywhere in them. So that one goes away, and then all of the ones down here go away. So that was step 1. Now we're into step 2. Draw that dependency graph and identify variables that are unreachable from S. Okay, so the dependency graph, how do we do that? Well, we're going to draw a graph with a node S, and notice S can go back to itself, so it's kind of a cycle going back to, so S can also go to variable A, so we'll draw an arrow from S to A. S can also get to B, so we'll draw an arrow from S to B. And then A and B don't really go anywhere. And then C loops back to itself, and C also goes to A, and C also goes to B. I'm missing a edge here. Here, I'm going to pause this temporarily and fix that, and I will be right back. Okay, and we're back, and I fixed the dependency graph. I don't like it when this doesn't match that, so if somebody looks at the slides, it'll be confusing. So in other words, here's our dependency graph. You notice S can go to A and B and S, so there it is looping back. There it is going to A and B. A and B go nowhere. C can go back to itself. C can go to A, and C can also go to B. So there's our dependency graph. Looks a little bit like a clown face now that I look at it, but anyway. So we draw that graph and we identify things that we cannot get to from S. So we start with S. Where can I get? I can get to S. Yeah, I can follow an arrow to get to A. I can follow one I can get to B, but I can't get anywhere else. I can't get anywhere other than S, A, and B. So C, therefore, is unreachable. And we can eliminate any production that has C anywhere in it. So in this case, none of these have C on the right-hand side. So all of these ones here, all four of these productions associated with variable C, those are all going to go away. So what's left now no longer has useless productions, and we're done. So notice that cut out a good portion of that grammar by getting rid of those useless productions. And now we're left with only the things that matter for this particular language. All right, one final manipulation we're going to do today. And those first ones are hopefully fairly clear and understandable why we'd want to get rid of those. And actually, just for a second, why do we want to get rid of useless productions? Well, it doesn't make sense to go down a path that's never going to give us a string in a language if we're trying to define a language. It's just going to run forever for no reason. And it also doesn't make sense to have parts of this that are useless and can never be reached, because what's the point of having, it's like building a room in your house and then walling it up so you can never get to it. What's the point of that? There's no reason to have that if you can't get to it. So we can just get rid of that and have a much smaller thing that only has the useful stuff. Now, left recursion. We want to look at eliminating left recursion from a grammar. Now, first off, what is left recursion? Well, a context-free grammar that is called left recursive is one that has one or more productions in the form A, some variable produces that same variable all the way at the left-hand side of the right-hand side, or the leftmost symbol on the right-hand side of the production. That's a left, any context-free grammar that has something that looks like that with any variable is a left recursive context-free grammar. So we want to identify any variables that have that property, where there's a right-hand side that has that variable at the beginning. And then we want to rewrite the grammar in such a way that the left recursion no longer exists. So as an example of a grammar that has left recursion, let's look down here. So S, here's the variable S. Are there any productions on the right-hand side that start with S? In this case, the answer is no. So S is not a left recursive variable. Moving on to A. Here's A. Are there any productions where the first symbol that we encounter, or the leftmost symbol, is that variable A? These how they have to, where they match. In this case, the answer is yes, A. So A is a left recursive variable. And B also is. Notice here's a production where it starts with B. So that's a left recursive variable. So in this case, we have two left recursive variables, A and B. And you can see that there. Here's the production right-hand side starting with the same variable that's on the left-hand side. Both true for A and true for B. Okay, so the process of removing the left recursion goes like this. Step one, we divide the productions of some identified left recursive variable into two sets. So in other words, if we have a left recursive variable A, some of the productions are going to be left recursive, some of them are not going to be. So we divide it into the two groups, the left recursive ones and the non-left recursive ones. Okay, so looking at those two groups, what we've done is notice that basically any one production that starts with that same variable we put it into that group, and then whatever follows that, we're going to call by the name x sub 1. And if there's more than one of these left recursive ones, we'd have x1 and x2. If there were 3 productions that had the variable at the leftmost symbol, we'd have x1, x2, x3. So we have however many of those we have. And then the non-left recursive productions, we list those out, and we're just going to call those y instead of x. And we don't have the a first on those, we just have the left recursive, or the non-left recursive part of that. And then what we're going to do is we're going to delete the a production altogether, get rid of all of them, and we're going to replace it with new productions where we have a produces yi, or yj in this case. So all of the y's, and we're going to add a new production for every y, that's that y with a new variable, in this case a prime, added on the end of it. So for every one of these y's that we have, we're going to list them all out, but we're going to add a pair production with it that has a new variable after it. So we have y1, or we're going to have a production that's a produces y1, another one that's a produces y1 a prime, a produces y2, a produces y2 a prime, a produces, and so forth, all the way up till we get to the last one where a produces ym, a produces ym a prime. So we're adding new productions for all of those, for all of the y. And then for that new variable that we just created, that a prime variable, we're going to add xi or xi a prime. So we're going to go through all of the x's, and we're going to add this, do the same thing. The x part followed by the x part called the new variable. And we're going to do that for all of them, for all n of the x's. Okay, so let's look at an example of that, and hopefully this will make a little more sense. So here's an example. So the first step, which ones are left recursive? A and B. So A, there's the A at the beginning. B, there's the B at the beginning. So we've got 2 left recursive variables, A and B. Notice S is not. S, there's none of these that have just the S at the very beginning, or the S at the beginning. Okay, so let's start with A. Since A was a left recursive variable, we write it out. There are 2 production groups. We divide them into groups, the left recursive parts, the non-left recursive parts. Now we're going to label those. This is x1, that's y1. Now we're going to get rid of all that altogether, and we're going to replace it with y1 or y1a prime, the new variable. And then a prime is going to be x1 or x1a prime. And since there's only one x and only one y, we only have 2 of each of these. And this represents the same language that this did. And let's pause there to think about that. Like, why does this work? And the reason why this works is if you look at the left recursive parts here, let's just focus on A for right now. What's going to happen when we go to replace variable A? Well, the possibilities are it's going to call one of the left recursive productions, which is adding an AA in this case in terminals, and then it's calling A again. So this is, if this keeps spinning around here and calling or doing this first production over and over again, we're just going to get a string of AA, 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 AA. Now, how do we ever get out of that loop? The way that we get out of that recursive loop there, it has to eventually end with this A, this single A over here, the non-left recursive part. So in other words, when I have left recursion, it's going to just make a string of those things that has to be ended at the front with a non-left recursive thing. So notice that's what we're doing. We're saying, hey, with A up here, it has to eventually be terminated at the front with a non-left recursive thing, when then it could have either recursed or not. So this is the case where it's not. This is the case where it recursed. And when it recurses, it just makes a string of left recursive things. So in other words, it loops down here. In this case, it loops here, making a whole bunch of these non-left or left recursive things, eventually ending with a non-left recursive thing at the front. Well, what we did down here is we pulled the non-left recursive things to the front and then added the string of it looping and creating a bunch of these things in a row down here. Pretty clever, makes sense when you kind of look at it like that. Now, let's go ahead and go to variable B. So there's B. it had a left recursive, divided into the two groups, left recursive ones, non-left recursive ones. So in this one, we're going to have x1 and y1 and y2. So now when we go to replace that, we're going to have b produces y1 or y1 b prime. And then we're also going to have y2 or y2 b prime. And then x, there's only one x, so we have that. So now let's rewrite the entire grammar with these things now substituted in for a and b. So the a and b are going to go away. We're going to get this stuff replacing it. So here's what the original grammar looked like that had the left recursion. And here's the grammar without the left recursion. Did not change the language. It's guaranteed not to change the language. But notice that there is no more left recursion in this. So note the language is the same, but the left recursion is now completely gone. And you might ask, like, why do we want to do that? Why would we ever want to get rid of left recursion? Because we've added extra variables here in order to get rid of it. This looks a little more complicated. Why would we want to get rid of that? And the answer for that comes down to later on when we go to write programs for these grammars. You might think, if you think about this grammar, this is kind of like a function call. Function S, when we call it, it could do one of four things. It could call generate a terminal A, and then call function S, and then when it returns from that, it could then generate a terminal B. Or it could generate a terminal B and call function S and generate a terminal A, or it could just call function A or call function B. Now, if you think about it that way, these are functions that can do any one of these things. Look at function or variable A here. Think about what function A would do. Function A, well, one of the possibilities is to, without generating anything yet, call function A. And if it makes that choice, it'll make that choice again, and you'll get an endless recursion here that'll just keep calling A over and over again until the stack gets destroyed. But notice down here, we don't have that. We don't have that way where we can endlessly recurse without generating any terminals. And the reason being that we've pulled the terminal, the ending one, to the front, and we generate that first, and then we do our loop after that, which is always generating things. And so now we've eliminated the possibility of that endless kind of function calling a variable, expanding itself endlessly. We've eliminated that. Now there are some other reasons as well that we'll see when we get to parsing later on. For example, you want to make a decision between these two things. How could I make that when I don't know what the beginning of A necessarily looks like? Because when I call A, it sees A. Down here, I call A, I can see a terminal. Here, I just see a variable. And so some advantages to getting rid of something like that we'll see when we talk about parsing later on. Okay, so that's it for today. Just be aware there may be a quiz next class. And you might ask yourself, well, what's the quiz going to be over? Well, I would review class 18 and class 19. This would be a safe bet. And speaking of things that are safe, make sure to wear a mask. Hopefully everybody is staying safe and staying socially distanced. But other than that, be ready for that quiz, and I will see you next time.